Hi, I'm Chia-Che, and in this part of tutorial, I will cover the multi-process support of Graphene Library OS. The core concept of the Graphene Library OS is to support the multi-process applications of Linux. In Linux, there are a lot of multi-process applications that either use fork or use SecDev'20 to run another program. And to support these applications in a confidential computing environments, we use multiple enclave that collaborates and acts as one single operating system to protect these applications. So think about if you have an application that has multiple processes. If one process, it will run inside one enclave. But if you have two processes, now each of the processes will run their own enclave so that they can be protected from the rest of the environment. In this cases, when the user look at these two processes, they need to identify these two processes as running inside one single operating system instead of seeing them as running in separate operating systems. So this collaborations of the libraries within two multiple enclave environments is extremely important. When talking about the multi-process support of the Graphene Library OSs, we usually use the term instances to indicate a multi-enclave environments created for one single application. So think about user A and user B. They both want to run their own applications inside the enclave environment. So in this case, user A could create a multi-process application. So suppose they have two processes, process 1 and process 2. Each process could have its own piece of library OS and also its piece of platform adaptation layers. So this process and library system platform adaptation layers would run inside its own enclave. So user A will have two enclave running inside one instance. The same thing as user B could have three processes running inside three enclave inside one instance. The idea of these instances is they are supposed to destroy each other. So the instance of user A will only trust the enclave inside that instance, and the instance of user B will only trust the enclave inside that instance. So in these cases, we will be able to identify the enclave that belong to the same application against those enclaves that belongs to other applications. The role of the graphing libraries in supporting multi-process application is to coordinate the states across multiple enclave. So think about an application with three different processes. You have a batch process, you have PS process, and graph process. In order to let these processes work together and provide you the functionality, they do need to communicate. They can use things like inter-process communication features, or they can use signals or pipe to connect each other. However, with supporting these kind of features, the library OS itself do have to act in a multi-enclave setting. So that means they do have to share states between each other's. However, the problem here is an enclave cannot share memory with other enclave. The physical pages between these enclave simply cannot be shared. So that led to a problem where library OSs need to share states, but they cannot share memory. So how would they actually coordinate these states necessary to share for things like forkings or IPC or namespaces? This would actually becomes a huge challenges. So Graphene libraries has solved this coordination problem by assuming there's no shared memories between these library assistants. So the idea here is instead of using shared memory to share states between these library OSs, you actually use remote procedure calls to send messages between these library OSs to coordinate the states. So with this design, you essentially make the Graphene library OSs a distributed operating system using remote procedure calls. We can use these remote procedure calls for sharing a number of stuff, including sharing the states of the namespaces, such as process IDs, or if you are forking a new process, you can migrate the current states of the operating system and applications through these remote procedure call to to other processes. We also support a number of inter-process communication mechanisms, including signaling, message queue, and semaphore. The only IPC mechanism we are not supporting so far is the System 5 shared memory. Process coordinations of the Graphene Lab process work as the follows. Let's use the Apache web server as example. The Apache web server has a multi-process mode. It can creates one process and use signals to communicate with other process. So think about, let's say P1 wants to send signals to P2. In this case, the kill system calls will be implemented by the library OSs using the PAL calls for sending remote procedure calls. And once the remote procedure call being connected and sent it will be sent through the pipe in the untrusted host operating system and be received by another enclave using the SGX PAL. In this case, eventually this will be captured by the signal handler, and this will trigger the actual handler inside the second process. So as you can see, the whole thing does not require sharing any memory between these enclaves, and the only thing you need is a pipe inside the host so that these two SGX PAL could send messages on this pipe. However, when running multi-process applications with enclave, it's important to ensure that any of these library OSs will not blindly trust any messages that come from other enclave. That's because all these messages are sent through a pipe in the untrusted host operating system. Therefore, the untrusted host operating system could potentially tamper with these messages or even create fake messages. Therefore, the only way of ensuring secure messaging for inter-process coordination is through a secure channels. We built this security channel using cryptography as well as the Intel CPU security features. So to create a secure channel for inter-process coordinations, we first would use the local attestation features of the Intel CPU. The CPUs will ensure that these two enclaves belong to the same instances. And then once they verify each other's attestations, they can use cryptographic techniques to exchange the encryption key and create end-to-end encryption channels. In these cases, whatever messages sent from this one enclave to another enclave inside the same instance, it will not be tempered or faked by the untrusted host operating system. To support multi-process applications inside enclave, we also extended the manifest syntax to support identifications of enclave inside the same instance. So think about this example. You have two processes, the batch program being in the parent process and the PS program being the child process. In these cases, because both the batch program and the PS program will be running in their own enclaves, so the enclave that run the batch program should at least be able to identify the enclave that run the PS program. So in these cases, we start with writing the manifest file of the PS program. In this case, the manifest of the PS program will have a regular manifest files including the loader information, the file system information, as well as the list of trusted files for SGXs. Once we finish writing these manifest files, we can sign this PS program, and then we can include the measurements of the PS program inside the manifest files of the batch program. In this case, the batch program will have pretty much the same manifest, except one more line. In this line, it will list all the trusted children of the batch program. So in these cases, when the batch program trying to fork or execute a new process, it will go through this list of trusted children and only create enclave that match with these measurement files. This will ensure that the parent process will only trust a limited list of child process and not trust any other enclaves that run other child processes. And so this will conclude this part of the tutorial. Thank you.